Jnanam paramam dheyam. Knowledge is supreme.
What we have learned so far is using D3H molecule, BF3 or carbonate, D3H molecule with 4 atoms, we have learned how we can figure out the symmetries of the normal modes without knowing what they actually look like. Because as we understood, we will not be able to say what the normal molecules look like just by looking at a molecule if the molecule is any bigger than carbon dioxide or water. Okay. But even without that, we have been able to figure out their symmetries. And then what we have been able to do is, to some extent, we have been able to assign specific internal motion, bond stretch and bend to these normal modes of different symmetry. Okay. If you remember, for BF3 or carbonate, whatever you like, which is D3H and 4 atoms, what are the symmetries of vibrations we had got? One was A1 dash. How many A1 dash? 1 or 2? 1. Okay. What is that A1 dash? We assigned that to symmetric stretch. And we can even draw it. It's something like this. Okay. Since it's symmetric stretch, it's not very difficult to draw it. There is no component of bond bend here at all. What was the other one dimensional representation we got? A2 double dash, right? And remember, why am I using small letters here? We said that we are going to use small letters for wave functions and normal modes in this case. We are going to use capital letters for states. When we talk about states next week, electronic states, or maybe on Thursday, you will see that we are going to use capital letters as well. But A2 double dash, what kind of motion was that? Doming motion. So, the way we drew doming motion was plus and these are minus or the other way round. Okay? The central atom coming towards you or going away from you, and the terminal atoms, the pendant atoms, making sure that the center of mass does not move. What else did we get? We got 2, what was that, E dash or E double dash? 2 E dash vibrations. And what are they made up of? In plane, bend plus stretch. In plane, okay, in plane, that is very important to remember, in plane. And when we talk about doming motion, do the bond lengths change? Do the bond lengths change in doming motion? Actually, they don't. There is no component of stretch there, right? If you remember, using the bond stretches as the basis elements, we got A1 dash plus E dash. So, only in these two symmetries you are going to see contribution from stretch. When we took doming motion, we got A2 double dash. So, doming motion is a pure change in angle kind of thing. It is just that it is not in plane, coming forward, going back, but there is no change in bond angle. Please let us have this very clear. And the other thing we got was using the 3 angles theta 1, theta 2, theta 3 as we wrote them in plane. We also got A1 dash plus E dash, but then we realized that A1 dash cannot be a correct solution, because if A1 dash is a correct solution, then all the 3 angles have to increase at the same time. It is not possible to do that, because theta 1 plus theta 2 plus theta 3 is 360 degrees. If theta 1 and theta 2 increase, theta 2 has no other option but to decrease. That is how we eliminated what we called a redundant coordinate, that was A1 dash from bending, and we had only E dash. But then in E dash, it is not possible for us to say that we have one E dash, one pair of E dash that is only stretch and one pair of E dash that is only bend. We cannot say that. Okay, it is a mixture. How do you find the coefficient of mixing? That is something that is beyond the scope of this course, unfortunately. That is done using Wilson's FG matrix method, and once you do that, you can actually draw diagrams like this. You might remember we had shown you the pictures of the normal modes. Now you see this is a symmetric stretch A1 dash. This here is the doming motion A2 double dash. Now if you look at these four, these two form E dash, one set of E dash, these two together form another set of E dash. And now if you look at the arrows, say this one, it looks fairly complicated, right? What does this mean? This is moving in, that is moving out, this is moving to this side, that is moving to that side. So first of all bond angles are changing. Besides, the lengths of the arrows are not all the same. So there will be distortion in bond length as well. This is kind of not very difficult to see. In fact, this is perhaps the best normal mode to look at, because this one is a bend, right? This is a bend. These two arrows indicate a bend, and this thing is going up, which says that the bond lengths are also changing. So here you see, I think this is where you see best how it is a mixture of in-plane bend and stretch. But how exactly you come up with these figures, that is something that we will not go to. We will stop at where we have reached so far. Okay. But from there we will embark upon another discussion, and that discussion is which of these normal modes are IR active, which of these normal modes are Raman active. Okay. Of course, as we know, in order to say whether a transition is IR active or Raman active, or whether a transition takes place or not, the condition that we have established in this course is that transition moment integral must be non-zero, right? Suppose transition moment integral is not zero. Is it still possible that the transition does not take place? Transition moment integral is non-zero, but transition does not take place. Is that possible? Yes. Example. So, you take the rotational levels J equal to 0, J equal to 1 for dihydrogen molecule. Well, transition moment integral is 0 there. Okay, that is not a good example. But well, what I am trying to say is, even if transition moment integral is non-zero, there might be some other factors that can mess things up. But for now, what we are doing is, at least is the transition moment integral non-zero. That is what we are trying to say. The question was, you have a particle in a box, right? Which transitions are allowed? Say that using symmetry. And this is something I think we had discussed in class, right? Even and odd symmetry. What was the argument we had used there? We had said that if this transition moment integral is something like this, I will write psi 2 and psi 1 this time. This is to be non-zero if and only if this triple product psi 2 mu, oh, I have written psi 2 twice, psi 2 mu psi 1, that remains invariant with respect to a symmetry operation. Remember, at that time we had only talked about parity, then we talked a little bit about inversion. Now that we know that a symmetry species means what is the response to every symmetry operation that is there in the point group, now we can expand a little bit. What will be our updated definition? What will be our updated condition for a transition moment integral to be non-zero? Yes, transition moment integral is non-zero when this is called a triple product of three functions. This triple product, what kind of symmetry should it have? It should be invariant with respect to each and every symmetry operation, right? Invariant means symmetric. So, which symmetry species is symmetric with respect to each and every symmetry operation? Yes? Identity element E. No, the capital E is only one operation. I am saying we have, well, totally symmetric representation is the answer. So, they are saying A1 is true for things like water, but then it is called different things in different point groups, isn't it? So, instead of saying A1, it is better to say the totally symmetric representation, because if there is a point of inversion, you will call it A1G. If there is a sigma H, very often you call it A1G dash, right. So, instead of saying A1, better say that this triple product must belong to the totally symmetric irreducible representation. This is the condition for the dipole moment, for the transition moment integral to be non-zero. So, this is the condition. This is what we are going to focus on for the rest of this discussion. And not only this, when we talk about electronic spectroscopy, we are going to make use of this as well. The condition for a transition moment integral to be non-zero is that the triple product, the two wave functions and dipole moment must belong to the totally symmetric representation. I can modify that a little more by saying that any one of the components of the dipole moment, right, where I can be x or y or z, right, because dipole moment can be in any direction. You have to resolve it into x, y and z. What is the symmetry of mu x in any point group? To which symmetry species will mu x belong? Mu x is along x direction. Sorry? No. This is a general question. You need to understand the question. And as I said, it is an easy question as always. So, give me an easy answer. What will be the symmetry, to which symmetry species or to which irreducible representation will mu x belong in any point group? Yes? Well, same symmetry species as x. Okay? Simple answer in simple words. Okay. Is that point made? Similarly, so what we are trying to say is that this triple product we can write as something like psi 2 x psi 1. If psi 2 x psi 1 belongs to the totally symmetric representation, then the transition moment integral will be non-zero. Or if psi 2 y psi 1 or if psi 2 z psi 1 belongs to this totally symmetric representation. That is the condition for the transition moment integral to be non-zero. Alright? Do we agree with this? Now, we need to worry about, when we are talking about vibrational wave functions, what is the symmetry of the vibrational wave functions? That is what we need to think. Now, when we talk about vibration, what is the transition, let us say we are talking about a simple harmonic oscillator. What is the only transition that we care about? Simple harmonic oscillator? V equal to 0 to V equal to 1, right? Well, the fundamental transition in the terminology that we have used. So, V equal to 0 to V equal to 1, that is what is important. So, here what are the wave functions that are important? The wave functions that are important are psi V equal to 0 and psi V equal to 1. So, if we are talking about vibrational transitions, then this is what we need to consider. What is the symmetry of psi V equal to 0? What is the symmetry of psi V equal to 1? Of course, everybody remembers what the wave functions look like, right? They look pretty much like, well, qualitatively they look similar to, but not exactly the same as the wave functions of particle in a box, right? So, but we will go a little bit deeper into it. Who can tell me what is the generic form for wave function of a simple harmonic oscillator? What is psi v? I will start. Psi v is equal to NV, yeah, multiplied by e to the power minus alpha x square by 2, and what is alpha? For our purpose, for now, alpha is a constant, we do not care, it is a constant, multiplied by HV. What is HV? Hermite polynomial. Yes, Hermite polynomial of x. So, if we are writing psi v in x, better write xi. We are talking about normal modes. So, instead of x, let us write xi square by 2 HV in xi. Actually, it is xi multiplied by a constant, but xi will work. Okay. So, this is a constant, we do not have to worry. What kind of a plot will this be? E to the power minus alpha xi square by 2. If I plot this against xi, it is a Gaussian function, right? It is totally symmetric. No matter what you do to it, it will not change. So, totally symmetric, we do not have to worry about this part. The only thing we have to worry about is what is the symmetry of the Hermite polynomial. Okay. So, and we only have to talk about two Hermite polynomials for v equal to 0 and v equal to 1. Who can tell me what is h v equal to 0 of xi? It is 1. Okay. So, the wave function is basically a constant with respect to xi, right? Well, not constant, you have this e to the power minus xi square by 2 as well, that is why the wave function looks like this. What is h v equal to 1 of xi? Since I have a poorer memory than you guys, I do not remember the coefficient, all I remember that it is some constant c multiplied by xi. Okay. Now see, so what is this? So, if can I write like this, psi 0 of xi, what will be the symmetry of psi 0 of xi? It is totally symmetric, right? Are we clear about that? Are we clear that for v equal to 0, the wave function is totally symmetric? So, this is totally symmetric. What about psi 1 xi? What is the symmetry of the v equal to 1 wave function? V equal to 1 wave function is a symmetric part, totally symmetric part multiplied by xi. So, what is the symmetry of psi 1? Yeah, antisymmetric. Do not forget, we are talking about a situation where you have many symmetry operations. Okay, it can be symmetric with respect to 1, can be antisymmetric with respect to 1. So, the generic, what would be the more generic answer, more general answer? Yes? Well, what if, well, even that is not a generic answer. No. Yeah, who said that? Hand? Symmetry of xi? You are right. That was the answer I was looking for. Whatever is the symmetry of xi, that is the symmetry of v equal to 1 wave function. Okay, there is no specific answer. It may be symmetry, totally symmetric, maybe e dashed, maybe double dash, whatever, I do not know. But at this point I can say same symmetry as xi. Okay. And now I come back to this problem. What do I need to determine? I need to determine whether this triple product is totally symmetric, or see, when I am taking triple products, usually you will not get a one dimensional representation. When are you going to get a one dimensional representation? If all three belong to one dimensional representation, right? Because then it will be 1 multiplied by minus 1 multiplied by minus 1, or minus 1 multiplied by 1 multiplied by 1, something like that. But suppose one of these belongs to a more than one dimensional representation, then the product is going to be reducible representation, right? So, what we are saying is this triple product must contain a totally symmetric representation. Yes. If it's one dimensional, if everything is one dimensional here, then you understand easily. Suppose it is not one dimensional. Suppose this belongs to a two dimensional representation, this belongs to a three dimensional representation, this belongs to a one dimensional representation. Then product will be 2 into 3, 5. But then usually 5 dimensional representations are not even there in most of the point groups, right. So, it will be a reducible representation, not an irreducible representation. I think we will understand it better once we start doing the examples. Okay. What does this rule boil down to? This part we have shown is totally symmetric. Okay. So, we are left with these two, isn't it? And this part, what is it? Psi v equal to 1. We have said it is the same symmetry as xi. So, the problem boils down to what is the symmetry of xi multiplied by x or y or z, isn't it? So, now the condition boils down to this product, direct product, this is called a direct product when you multiply 2. Xi x or xi y or xi z, these must contain the totally symmetric representation. Is the problem defined? Is the problem defined? Yeah. So, this is the condition for IR activity, that direct product of the normal mode of vibration and one of the Cartesian coordinates must contain the totally symmetric representation. Okay. Before we take the examples, we will simplify it a little more. This is our condition then. So, what we will do is we will quickly derive another small working rule that will make our life a little simpler. So, we are talking about a product, right. So, let us say I am talking about a product AB. Okay. A is xi and B is x or y or z. What is chi AB? This is something we have done earlier. What is the character of a product? Sum or product? Product of the characters, right? Product. Chi of A multiplied by chi of B. Okay. What do we require? We require that this character I think I've suddenly started writing in a different convention than what we have used so far. I think that is a problem. So, I'll write like this, sorry. I'll write like this, sorry. Chi AB of R. This is the convention we have been using, isn't it? Inside brackets, we always wrote the symmetry operation, right? So, chi AB of R, that is the character of the function which is the direct product of A and B, that is equal to chi A R multiplied by chi B R. So, what does this condition boil down to? If it is totally symmetric, then, and let us work with one dimensional representations, it is easy to understand, just believe me that it can be carried on to multidimensional representations as well. So, if we are talking about one dimensional representations, what are the characters, what are the values the characters can take? +1 or -1, right? Now, if this AB belongs to a totally symmetric representation, what should be the character of chi AB for any R? Totally symmetric representation, what is the character no matter what the operation is? +1, right? Right or wrong? Totally symmetric representation means something that does not change as a result of any symmetry operation. So, no matter what R is, this should be equal to 1. Okay. Now, we are working with one dimensional representation. So, chi A of R, what are the possible values? +1 or -1? What about chi B of R? +1 or -1? Right. So, what are the possible combinations? 1 1 minus 1 minus 1 1 minus 1 minus 1 1. In these two cases, of course, the product is not plus 1. For the product to be plus 1, both the characters have to be plus 1 or both characters have to be minus 1. Okay? Are we clear so far? Now, I am going to make the general statement. The general statement is a direct product contains the totally symmetric representation if and only if the two functions of whose product we are taking, the two functions belong to the same irreducible representation. Do we agree? Do we not agree? I take a direct product. Let us talk about one dimensional representation for now. If the direct product has to be totally symmetric, then it is imperative that both the functions participating in the product belong to the same symmetry species. Do we agree with that? Okay. We can demonstrate with our old friend C2V character table. Good thing about C2V is everything is one dimensional. Now see, convince yourselves. Suppose I have A2 and B2. A2 and B2. What are the characters? 1 into 1 is 1, but then 1 into minus 1 is minus 1. So it cannot be totally symmetric. But if it is A2 and A2, 1 into 1 is 1, 1 into 1 is 1, minus 1 into minus 1 is 1, minus 1 into minus 1 is 1. Same is true for B2. If both the functions belong to B2, 1 into 1, minus 1 into minus 1, minus 1 into minus 1, 1 into 1. If there is a question, please ask now. The point I am trying to make is that a direct product contains a totally symmetric representation if and only if the two functions belong to the same irreducible representation. Once we are convinced about this, we will make the statement about IR activity. If there is a question, this is the time to ask. Do we have a question? Any question? Yes. I said that product of I said that product of x with xi, where xi is a normal mode, or y with xi, or with of z with xi, one of these direct products must contain the totally symmetric representation. That is what I said. Not necessary. All cannot. If this is the case, see what have we shown? That they have to belong to the same symmetry species. You look at the character table that is given here. X belongs to B1, Y belongs to B2, and Z belongs to A1. So all three simultaneously cannot satisfy it, but at least one of the components of dipole moment should contribute to the transition. That is what we are saying. It is impossible usually, unless X, Y, Z belong to the same symmetry species, it is impossible that all will be non-zero, and we are going to make a statement about that as well. Do we have a question? So, the statement that I wanted to make is that the normal mode must have the same symmetry as either X or Y or Z in order to be IR active. Are we clear? Okay. So, in that case we come back and we proceed from here.